Okay, so I'm going to do one example using the Arrhenius equation. This is an example where you have kind of collected some experimental data and you're trying to figure out the activation barrier. All right, so here's our experimental data. Where is our experimental data? I've lost my mouse. Well, our experimental data is in this table, right? So we have entry one, come back here. Entry one, entry two, entry three, and entry four. And notice that we've run the reaction at various temperatures. We've figured out the rate constant at each of those temperatures. So we have a T1, a T2, a T3, and a T4. What we need to do is convert these to 1 over T, where T is in Kelvin, and then also calculate the natural log of K. I guess technically you don't have to calculate the natural log of K right away, but we'll do it at some point. I'm just going to do entry 1 and entry 2, or I'm going to do entry 2 and entry 4. So for entry 2, 1 over T in Kelvin ends up being 2.12 times 10 to the negative third, right? So now to figure this out, of course, we're just taking the temperature in Celsius, adding 273.15 to get it into Kelvin. So that comes out to about 472-ish, right? And then taking 1 over that number to get the 1 over T in Kelvin. We do the same thing for entry 4, right? 251 degrees. We add the 273.15 to get to 512.3, I think. Yeah, something like that. Nope. 524.3. I'm bad at arithmetic, apparently. 524.3. 1 over that number then gives us our final 1.91 times 10 to the negative third. Right? So this is going to be our T1. This is going to be our T2. And we'll save the ln of K for later. Right? Because when we do this, right, our formula is ln of K2 divided by K1 equals negative EA over R times 1 over T2 minus 1 over T1. So now we have values for each of these. 1 over T2 is 1.91 times 10 to the negative third. Minus 1 over T1, which is 2.12 times 10 to the negative third. The activation energy, that's what we're trying to find. And then the R value is the 8.3145, right? That's the gas constant. On this side of the equation, we have the natural log of 2K values. So K2, right, this is going to be K2, and this one is going to be K1, right? K2 is I left out a negative. You guys got to keep me honest on this stuff, right? K2 is going to be, where are we? 3.16 times 10 to the negative third divided by 5.25 times 10 to the negative fifth. All right, so we do all of this, and what we end up with is I divide these numbers and then take the natural log, and what I get out is negative, or sorry, that's a positive number, 4.098. That equals negative EA over 8.3145, and then I take the subtraction over here, and I get 2.1 times 10 to the negative fourth. Okay. And now I just need to move all this stuff over to, I left out a 5. I just need to move all this stuff over to the other side, 2.1 times 10 to the negative fourth, the negative sign and the 8.3145, move that over here to figure out my activation energy. And what I end up with is my activation energy equals 1.62 times 10 to the fifth joules per mole. Right? Or if you want to express it in kilojoules, right, you can divide by 1,000. You get 16.2 kilojoules per mole. Right? Either answer would be acceptable. Right? We can all do scientific notation. But this is a kind of thing, right? It's a lot of math, and you have to use a lot of kind of scientific notation because you're going to end up with very small numbers for your 1 over t's, and your k values are usually in scientific notation, right? So it's kind of cumbersome to deal with all these like 10 to the whatever powers and such. But if you do it correctly, It's just algebra, and it's just arithmetic once you get all that stuff in there, and then just moving stuff from one side to the other, and we can get this kind of thing. But this is the kind of thing that you're going to see, right? So what we notice here is that we have multiple temperatures, and if I set this up right, you can take any of these entries. You could take entry 1 and entry 2, and you should get a similar answer for the activation barrier, right? I chose 2 and 4 because that's the one that I had written down, right? But the key is we have multiple temps and we have multiple Ks, whoops, multiple rate constants, and we're looking for activation energy, right? So in a question, when you are kind of evaluating your question and trying to figure out which formula do I use to answer this question and that kind of thing, right? When you see those, this is the kind of thing that you want to look for. You want to look for clues like activation energy. Anytime you see activation energy, the answer is going to be Arrhenius equation, right? Because that's the only way we know how to calculate that activation energy at this point. I think that'll be the only way that we really do it going forward. Right? If you see multiple temperatures, that's another clue because the Arrhenius equation is all about multiple temperatures, right? So look for those two things when we do this, and that will be your clue to use the Arrhenius equation. Obviously, the tests and stuff are open book, open notes now at this point, but if you do, there is an equation sheet available on D2L. I will put a link to it on the news post next week. But the Arrhenius equation in all its forms is available on there as well. So if you want to look it up and just be sure that you've got it copied and down right or whatever, it's on there. You can find it there. I highly recommend doing that and using that when you do your exams because you want to make sure you have the right formula. So I hope that helped kind of see how these things go through, what kind of math is going to be involved doing that. If you have additional questions on activation energy and that kind of thing, please let me know. And I hope that this all makes sense. So I'll see you next. We're going to get into equilibrium, what happens when we have rates going in the opposite directions of each other. So that'll be the next thing. We'll see you in the next video.